Okay, so as mentioned on the last video, on this video we will start to discuss about forward and inverse kinematic equations and be more specifically about orientation. This whole time we are talking about forward and inverse kinematics equation in terms of position. And introducing this topic, we will discuss this in terms of orientation. So again, I will use the content of the book to introduce this topic. So let me write. We will discuss about forward and inverse kinematic equations. Orientation. Okay, and to introduce this, I will use the statement, the content of the book. So we have to suppose that the moving frame attached to the hand of the robot has already moved to a desired position in Cartesian, cylindrical, spherical, or articulated coordinates, and is either parallel to the reference frame or in an orientation other than what is desired. And to now we understand and we know all these terms. A moving frame attached to a to the hand of the robot. So this is other subject. Let me drag this a little bit to up. So let's draw a robot arm and doing again an analogy to a vector, and we can even draw the system in which this robot arm is localized, is placed. Right here we just wanted to draw the moving frame, and usually this moving frame, which is a reference frame, is the frame NOA. So right here is the hand of the robot, and attached to this hand we got this moving frame. And as as told to you, I'm keep saying this all the time, and it's good because this way you will fix it. Right here on the origin of this vector we have this other reference frame, the universe reference frame. So let's say we can write a transformation of the H frame in relation to the U frame, something like that. Okay, so we are doing the interpretation of this statement, and again is the description of the task that the robot is doing. So at this point you know that it's very important to know how to interpret these statements, these descriptions. And the next step is to rotate the frame appropriately in order to achieve a desired orientation without changing its position. So let's see. Um, I will have to draw this again. Now let's draw with the coordinate system. X, Z, X, Y, and X. Okay, and attach it on the hand of the robot, another reference frame. Okay. Right, here's the hand. The hand and the universe reference frame, and we can call as well of R. And so first we attached a moving frame on the hand of the robot. Has already moved it to a desired position in the Cartesian, cylindrical, spherical, or articulated coordinates, and is either parallel to the reference frame or in an orientation other than what is desired. The next step is to rotate the frame appropriately in order to achieve a desired orientation without changing its position. So this draw that I have made is a draw of the most simple one, the most simple robot that we can have, which is just a simple link doing changings on its position. Actually, we can do translations with this robot on this respectively axis. We can translate to the above the z-axis. We can translate above the y-axis, and as this is just a simple arm with just one link, and I'm saying as well that is fixed on the region of this reference frame, is a limited robot, okay? But well, if it is fixed, we cannot. Okay, it's fixed, but I'm saying that you can do translations. Okay. Well, we can change. We can say that it's fixed, and again is a device, a mechanism with the ability to stretch itself. So let's say we were right here, and this is three-dimensional, and but this I don't know, it is only going to move. Let's see, right here, again, it is good to have a sense of views. right here we are on the XY plane. Right here is on the ZY plane. And in which plane this robot arm is localized? Um, is three-dimensional, so is at the same time or on both planes because it has the dimension of length, it has the dimension of width, and also a depth, something like that, and we can decompose on the y-axis, on the z-axis, and also um, on the x-axis, something like that. But let's keep trying to interpret this statement. Let me see. And the next step is to rotate the frame appropriately in order to achieve a desired orientation without changing its position. Yeah, we can rotate the hand of the robot. We always can do rotations. Okay, so if we do a rotation on the end frame, on the end effector, where we have attached a reference frame, this way we can change its orientation. So doing this rotation, but right here we have rotated the frame. At least we got right here a 2, which can be a hand. So this is the arm, which is a link. And right here we can have a hand, which is a 2. A 2, which can be a hand. And is for grab, pick and place, etc. Okay. So this can only be accomplished, be able to do a rotation on the frame, on the end effector, without changing its position, only the orientation, and this can only be accomplished by rotating about the current frame axis. Rotations about the reference frame axis change the position. So it's something like we have just to rotate this frame, and let's say right here we got let me divide this in one link and 2 links, and this link right here, let's say let's change for a cylinder, and now we can do other types of transformations, but we don't want it to change right here the position of the factor. We just wanted to change its orientation. So we have to do a transformation of rotation above on this current frame, okay, not on this one. Okay, the appropriated sequence of rotations depends on the design of the wrist of the robot and the way that the joints are assembled together. So right here we will introduce this concept. Also, we are talking about paths. Um, this statement is saying that we wanted to change the orientation of the interfactor without change its position. So right here we have done a adaptation. So I place it right here, a cylinder. So if we do a rotation, but only this link it rotates, and maybe right here we will need another joint. We need to make that this frame, it doesn't change its position. Right here on this frame, this attached frame on the end effector, which can be and where is also attached a tool like a hand, which is the more commonly tool of that we attach it on the end effector of a robot. We only wanted to change its orientation. So right here we have done a rotation, and this is what we want right here, is just change its orientation. And if again, if we do a transformation of translation, obviously we will change its position, and this is not what we want. So we will introduce the concepts of row, pitch, yaw, and they are used together. RPY. Those are angles. And we got Euler angles. And articulated joints. Okay, now we have to introduce these concepts: row, pitch, and yaw. Angles. So this is a sequence. of 3 rotations, about the current A, O, and N axis, just like we have done right here. Okay. Which orients the hand of the robot. To a desired orientation. The assumption here is that the current frame is parallel to the reference frame before the application of RPY. Otherwise, the final orientation of the robot's brain is a combination of the previous orientation post multiplied by RPY. To maintain the position of the frame and only rotate it to the desired orientation, we post multiply the frame by the RPY matrices. And now we got the sequence made it of 3 rotations, and the sequence is a rotation of phi, and superscript we have the A, so is a rotation of phi on the A axis about the A axis. Z axis of the moving frame. And this is the row. And we got another rotation with the angle phi, but now is on the O axis. And is on the moving frame Y. And this is pitch. And now the last rotation with a angle phi on the n-axis. Okay, n is on the moving frame x. And this is yaw. Okay, so let's see something. Let's draw the XYZ coordinate system. And also the NOA coordinate system is more a reference system than a coordinate system, the way that it's used. NOA, A, O, and N. And if we put them parallel to each other, so Z, A is pointing on the same direction as Z, O is pointing on the same direction as Y, and N is pointing on the same direction as N. So let's see if this analysis is correct. So for O we have Y, it's correct. For X we have N, and for N we have O, for O we have Y, and for A we have X. Both are correct. Okay, so we have done this analysis correct. And actually I'm already has draw something. As you can see, from now we will use these angles of rho, pitch, and yaw. Those are angles, and we will use these angles. So it's important to see that in what axis the frame is pointing. Like right here, we have to see in which direction the A axis of the frame, which can be a moving frame, and which direction is pointing. It's pointing on the same direction Z, Y, and X, and we know that A points on the same direction as Z. Okay, so after done this analysis, we will use this analysis together with this introduction of these angles, rotation, rho, pitch, and yaw. And if we know the direction that this axis of this moving frame FNOA is pointing, so we already has solved something very similar. This way we can construct the matrix which symbolize this transformation. So when we are doing a rotation, we are doing a transformation, and this transformation, it will generate a some certain angle. So if we are doing a rotation um, above, right here, as you can see, above the or around the a-axis of this moving frame, we will generate this phi angle in relation to this a-axis, and as it's pointing on the same direction as the z angle from this reference frame, we can use its characteristic rotation matrix of the z um, axis and adapt to the a-axis. So this is what we are doing right here. We have used the characteristical rotation matrix above the z-axis, and we have adapted to the a-axis, and of course with the phi angle, and again adding the scale factor w. And we have done the same for the n-axis. So n-axis is pointing on the same direction as x-axis. So we have used the characteristic rotation matrix, which is made it the rotation that is made it above the x-axis, both above the x, the z and y-axis, they have a characteristic rotation matrix. So we use this characteristic rotation matrix to adapt to the axis of the moving frame, and using its respect, respectively angles, the phi angles. Okay, and the o-axis is pointing on the same direction as the y-axis. And now we have to get back on the beginning of this video. I was bringing this concept of row, pitch, yaw, and why. This is like another technique. Again, right here in robotics is pretty much text interpretation. Imagine that now as a somebody that is going to do some project, something on the robotic area, and what a robot does. Robots does tasks. So you are being hired to do the programmation of a production line. So you have to pick the robots that it go realize the tasks, perform the tasks on this line production. So it's a line production. Let's imagine the one of the most simple ones. I don't know. Pick and place parts and objects is one of the most simple tasks that a robot can do. So let's say is a 1D or two-dimensional 1 degree of freedom robot or 2 degrees of freedom. So we are only working on the XY plan. So it just goes to up and down and pick something and transport to another area of this line production. Um, in this example, I think maybe it doesn't even is applied right here, because right here what we wanted to do again is do a rotation on this moving frame, which is attached on the hand of the robot. Is a reference frame, and we don't want to change the position. We just wanted to change its orientation. So for that, we have to apply the angles of roll, pitch, and yaw. So it's more like a technique again. So we are learning about techniques. In this way, let's see. Right here, to maintain the position of the frame and only rotate it to the desired orientation, we post multiply by the frame. We post multiply the frame by the RPY matrices. Okay, so it's been a while since I don't bring any software. And this is not even the software that I wanted to present to you. I was thought I was thinking in other software to present to you, but we can use this. So we are seeing something like we wanted to change the orientation and not the position, and now you know that we can do change on the orientation if we apply what type of transformation? Rotation ones. So let's see. The analogy with the draw that we have made. So we have three links. One link, the second link, but we have joints as well. But right here is one link, two links, three links. Right here is another link, and this one is a link too, because is a bodied with this division. Right here is a division. So we have three links. This is a joint. We can call it joint. Right here, another joint is a joint as well. Or if it's not a joint, but is a link that we can apply a rotation. Okay, so we wanted to do a rotation on this hand without change its position. So let's see. Is what we are doing right here. We are doing rotations. And change its orientation, and not changing the position. But this is programmed, okay? It's a simulation. We are doing a simulation, and if you can see right here, all line angles. We are changing the angles. Okay, and as this is a simulation, and now it's going to be very interesting. Let's say you wanted to program this interface. You wanted to program this the simulation. So you have to write the transformation equation, which will allow um, the simulation. And I can say that if you wanted to do this type of thing, you will use Java, because Java allow us to do simulations and animations. Okay, so it's kind of a algorithm. So you have to write a algorithm, and the algorithm is the matrices, and you have to write these matrices in a form of a algorithm and apply programmation using Java. So I think this way you are able to do a interface or simulator just like this one. Okay, so this way we are changing its orientation. So now the end effector is right here, and if we change the orientation, changing this data angle will change right here the orientation, and the position is going to remain the same. But I don't know. Let's see. And again, if I'm wrong, I will try to correct me on the incoming videos. And exactly. And this technique of doing a rotation without changing the position, it consists of post multiply. Let's see, we have to post multiply. So we post multiply the frame by the RP matrices, and is exactly what we are doing right here. So right here is because I was using the Portuguese literature, but actually is RPY, row, pitch, and yaw. Okay, and let me take the characteristical rotation matrix. Let me find them. Right here, the characteristical rotation matrices above the X, Y, and Z axis, respectively. And as you can see, let's see, for this one is for X. So we have just changed, we just have to change the angle. Right here is theta, and we are substituting. We are doing a adaptation to the matrix. Okay. And for Y, this one, okay. this one for Z. And we have to do this operation of multiplication between these matrices. And again, we will use the octave to evaluate this operation. And we can also do by hand. But this we will do on the next video. And I will watch this video as well. And if I did something wrong, I will try to correct me on the next video and finish with this explanation and start to think on the examples, how to solve them. And for now, it's all. Thank you.